Good day, everybody. This is a practical application of transition matrices. So we're going to be given a scenario, and that scenario is, get my pen to work, where are we? Is we have two fast food outlets. Jill and Pete's are located in the same small town, and we're given a series of information about the transition of customers between the two restaurants. So we have 80% of people who go to Jill's return the next week. So we've got that there, 80% coming back to Jill's. 20% who start at Jill's, they go to Pete's the week after. And then with Pete's initial customers, 25% of people who go to Pete's go to Jill's the next week. Just there. And then 75% return to Pete's the following week. So the first thing, part A, we're asked to construct a transition matrix to describe this situation, to describe this network here. So for part A, the first thing we want to do is we know it's a square matrix, a 2 by 2. So we've got Jill and Pete's, and then brackets in, and then Jill and Pete's here. So this is where they start, and then they finish here. Okay, so that's all the finish, that's where they go to. So from Jill to Jill, we know we've got 80%, so 0.8. From Jill to Pete, and we have 20%. That column has to always equal up to 1 or 100%, because we have 80% of the people who start here, doesn't matter how many, go back to Jill's. The 20% must end up somewhere else, so they go to Pete's. Then from Pete's, the people who go from Pete's to Jill's was 0.25, and from Pete's back to Pete's makes up that to 1 again, and that's 0.75. Okay, so it's an important thing that all the columns add up to 1. The rows do not have to, but the columns do. Okay. Initially, 400 people eat at Jill's and 400 people eat at Pete's. Write down a column matrix SO that describes this. So for B, SO is going to be equal to 400 and 400. Okay, that describes how many are eating at Jill's and at Pete's. And after that, we have part C. How many of these people do we expect to go to Jill's the next week, and how many to Pete's? So for part C, we can come up here. Not sure how that he's ended up there. Let's get rid of that. Part C. So the number that end up there the next week is going to be equal to Sn plus 1 is equal to T times Sn, and that's where SO is equal to 400, or the initial state, and 400. Okay. So we're going to take our transition matrix, which is the one just here. So this is T, our transition matrix. This is SO. In my CAS, I'm going to call it S. And once we've got that, we will find out after 1 what's that all equals. So if we want to look at it properly, we would go SO plus 1 is equal to 0.8, 0.2. Okay, I'm back. A little bit of an interruption. Kids yelling out the background, but it's all good. So we're setting up our matrix. So our first state after the initial state, which is 400 and 400, it's going to look like this. So 0.25, 0.75, and that's all times by S0, which is 400 and 400. Okay, so the elements of this are, pick the right pen. The elements of this are, we've got the transition matrix times S0. Okay, we've got S0 there. That's all going to give us S1 being equal to whatever it comes up with. So I'll pop over to our CAS. I've put in those two elements already. I've named them, so I can simply go and do T times S, and it comes out that we have 420 and 380 as our answer for S1. Okay. How many do we expect to go to Jill's after 5 weeks, and how many to Pete's? We can continue this recurrence, or we can set up our rule for this one. So our rule is going to be n equals Tn times S0. Okay, so this time that's all going to equal T to the 5, power of 5 times S0. And that'll give us our fifth state, or after 5 weeks. So over here, T to the power of 5 multiplied by S, and we get 442 and 358 to the nearest whole person. Okay, so that's how many we expect. So if we couldn't leave that in the that format though, for the sake of an answer. We'd have to say that Jill would have 442 and Pete would have 358. Okay, so the order of these two, the 400 and 400 in the initial state matrix, is the same as the output here. Okay, that we've got J and P and J and P there. So we'd have J and P up there. And last of all, in long term, how many do we expect to eat at Jill's each week? How many of these people do we expect to eat at Pete's? So for part E, we want to find 2 consecutive values for N that are going to give us the same number of people attending the restaurants. So if we head over here, let's start with T to the power of 20 times S, and then T to the power of 21 times S. Compare those two. Okay. And that's a reasonable start. So long term, it doesn't say when it has to start, but for when n equals 21 and 22, we've already got common whole numbers there. So Jill will have 444 and Pete will have 356. Okay. And look, we could continue that, doesn't matter. To the T to the power of 22 times S. And you see we just get closer and closer to, or it sticks to those figures as whole numbers. Okay. Hopefully that helps with the application of transition matrices and states. Okay, so this is our state, or our initial state is down there. Okay, so that's our initial state, and we've got a transition there. We've set up a recurrence relation for the first one. Okay, there, and that gave us that. For the next one, because we're going 5, sometimes it's easier once we get that high to set up our rule. It takes a slightly different format, and then hopefully we're getting used to needing 2 consecutive values of n to give us the same outcome. Okay, and that was done here successfully. Hope that was handy. If you liked it, give it a thumbs up. If you have a question, feel free to pop it in the comments, and subscribe if you want to jump onto and check out the videos as they come up. Have a good day, gang.